In this example, the rigorous approach is used to determine the effect of temperature on the equilibrium constant for the reaction where gas phase ethylene is hydrated to form ethanol, all components in the gas phase. We are going to apply the simplifying assumptions that led to the development of Van'tHoff's law. Okay, make sure that you can still recall what they are in order to determine the equilibrium constant for this reaction at 145 degrees Celsius, and then we're going to compare our answer to that in Smith, Van Ness and Abbott. From data given in table C4 in appendix C in Smith, Van Ness and Abbott, we can find the standard state Gibbs free energy of formation of each of the components, as well as the standard state enthalpy of formation of each of the components, specifically given at 298 Kelvin. We can now use this information together with our equations for the standard state Gibbs free energy of reaction and heat of reaction in order to calculate those values at 298 Kelvin, or units in this case in joules per mole. So now we can calculate the equilibrium constant at 298 Kelvin. According to Van'tHoff's law, we can now calculate an equilibrium constant at any other temperature by taking the linear approximation. Since we assume a constant value for our delta H, remember it's going to be minus times minus, so it will be a plus. This needs to be in Kelvin, so it's 418.15 Kelvin in our case for 145 degrees Celsius, which gives us a value for the equilibrium constant at 145 degrees Celsius of 0.144. which is pretty much the same as the value obtained by Smith, Van Ness and Abbott when they followed the more rigorous approach. It is easy to get confused with the signs in Van'tHoff's equation, but we can always apply the reasonable person test to our answers. This reaction is obviously exothermic if we look at the heat of reaction. So according to Le Chatelier's principle, with an increase in temperature, we expect that the reverse direction of the reaction will be favored. And therefore, at a higher temperature, we have a lower equilibrium constant for the reaction as written in the forward direction, which is true for the answer that we obtained.